Hey, Nathan here. Welcome back to another game math video. And in this video, I'm going to discuss the mathematics and algorithm behind per pixel collision detection. Now, if you're working on a 2D game and your game objects, your pictures, your textures are all square, they have no transparent pixels, you can ignore this per pixel collision detection. The reason you will want to use per pixel collision detection is if you're running a game and you have game elements, textures, images that have transparent pixels, like you have circles in your game. Every image needs to be a square. So in order to draw a circle, you have to have transparent pixels on the outside of that circle. So we use per pixel collision detection to determine if these circles have collided. You don't want to have a collision if they're both intersecting on a transparent pixel. You want to have it actually collided when the object actually collides. So the circle collides with another circle, or a circle collides with a square or something. And this is just one of the many ways of doing a more in-depth collision detection than just a rectangular collision detection. So I'm going to bring out my colors here, and I'm going to choose, let's say, white. So no matter what the image is, no matter what the texture is, it's always going to be represented square. So I'm going to draw a white square here. And even if it's a circle, even if it's just a single little, if it's triangle, any object, any shape, anything in that picture, it's always represented as a square. And the picture has pixels associated to it. So think of the picture as a grid. So I'm going to draw lines here, then I'm going to draw lines vertically as well. So each one of these little squares is considered a pixel. Alright, so let's bring up here and let's draw a yellow one. So I'm going to do an intersection here, and I'm going to draw a yellow line from here and here. So we know it's intersecting, but we don't know if the actual object is intersecting or not. So I'm going to draw a line here, 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 and here. Vertical line. Okay. So let's draw that line a little straighter here. Okay. So each one of these boxes is a pixel. So we need to actually loop through every single pixel. Let me change this to green. We need to loop through every single pixel in a texture to see if it has collided with another pixel in the other texture. So we do that. We loop through we choose one object. Usually you want to choose the one that's smaller, because we're going to have to loop through every single pixel. So when you're looping through one of the objects, let's choose the yellow object here, right, which is red. So when you loop through the yellow object's pixels, you need to choose the first pixel on the yellow texture and loop through all the pixels until the last one, which is here. Now you're looking at that on the yellow object, this one here. We need to convert that, whatever pixel we're looking at, we need to convert this one. Let's say we're at this pixel now. So we look at that pixel. we need to convert that to this object. So we have a red, we're investigating this pixel here. We're investigating the yellow pixel. We can see that it is inside of our yellow object. Now, what does that pixel look like in terms of the white object's space? This object. That is nowhere near that object. So that is not even close to object. So that is not in the object, so we can say, all right, that pixel is not part of the per pixel collision. So we can continue on to the next pixel, which would be this one. So that pixel, that is inside of white as well. That pixel is also inside the white pixel. Now, once we know that that pixel exists in both objects, we can test to see either the alpha value by a certain amount, certain threshold, like 30%, or if it's just 0, we can continue. If it's not 0, we have a collision. So let me clear this out. Okay, so let's walk through this again. We have one object here. Let me make this a little bit smaller. And we have another object here. Okay. We pick the one that's the smallest, or if they're both the same, it doesn't matter which one we pick. So A is 1, 2, 3, 4, 1, 2, 3, 4, 5. So it's 4 by 5. And B is 1, 2, 3, 4, 1, 2, 3, 4. So 4 by 4. So let's choose B to be our source. So this one, B, this is the one we want to look at every single pixel. We want to choose the one that's smallest because we need to investigate potentially. The loop might potentially investigate every single pixel inside of that image. If you have one very small image and one extremely large image, you want to use the one extremely small image. That way your code won't be bogged down by looking at the bigger image when you can optimize it by looking at the smaller image. Either way, it's going to be a collision or no collision. It doesn't matter which one you look at first. You can have a 1 pixel by 1 pixel image, and you can use that instead of a 200 by 200 pixel image. Alright, so the first thing we need to do is we need to loop through every single pixel in the B's object, the yellow object here. So we start out with pixel at index 0, which is this one here. We need to convert that, so X in B is at index 0, 0. So X relative to B is at index 0, 0. All right, X, we need to convert X relative to A. So X relative to A is equal to 2, 4. So 2, 4. Index 2, 4, because everything starts at index 0. So this is 0, 1, 2, 3, 0, 1, 2, 3, 4. 0, 1, 2, 3, 0, 1, 2, 3, 4. So 2 is this, 4 is this. So we got 2, 4. So we need to look at x, b's color and x of b's color and x of a's color. Now we're actually going to do something different here. What we want to do in our tutorial coming up is to get a intersecting rectangle. So we have B here. So we know A intersects with B. So what we want to do is get an intersecting rectangle. And what that will be, that will look like this. We need to get the intersecting rectangle, and let's bring up the actual formula here. So, intersecting rectangle. Left is equal to the maximum of the two left values. So max A dot left, comma B dot left. That is this here. The maximum of the left. The maximum of the left is B's left side. A's left is here. B's left is here. B's left is further to the right, so it's the maximum. The top is equal to the max of the y, the top. So A dot T and B dot T. The maximum. Again, the maximum. This is A's top. This is B's top. Maximum will be going downwards, so again, it will be here. So that is the top of that rectangle. Right is equal to minimum. The minimum of the right. A dot R, B dot R. So the minimum of those. The minimum of the right. This is B's right. This is A's right. Right here. That is the minimum. So we know the left and top and the right now. So it's going to look like this. This is the intersecting rectangle so far. Now we need bottom. Minimum. A dot bottom. B dot bottom. The minimum. B's bottom is here. A's bottom is here. A's bottom is less, so that's the intersecting rectangle. Now, what we need to do is loop through every pixel in the intersecting rectangle. But we still run into an issue where one of the, we will get 0, 0 in some cases, or this is 0, 1, 0, 1, 2, 3. So we'll either get 0, 0 because we're looking at B, or we'll get 1, 3 if we're looking at A. And 1, 3 in terms of B will be different. So we need to add more to the algorithm. As we loop through, we need to get the source color and destination color. So we know that in intersecting a rectangle, we know all the pixels will be valid. So we don't need to see if a pixel will be outside. We're not going to be testing this pixel, so we don't need to test to see if it's outside of A. So as we're looping through every one of these pixels in the intersecting rectangle, we need to get the source color and the destination color. Alright, so I paused the video so I could set this up for you. I created an A texture and a B texture, and then the intersecting rectangle in here. The values are listed here for X, Y, W, H, width and height, X, Y, width and height, and X, Y, width and height. So the intersecting rectangle is here. It starts at 12 and 26, and it goes 8 pixels wide and 4 pixels high. So we need to loop through every pixel in I and get them in B and A's space. So what we need to do is check to see the intersecting rectangles X, Y. So X, Y, that will be 12, 26. So that will be this here. So we're going to look at this pixel here. That's 12 by 26. So let's make a room here. 12 by 26. So 12 by 26. That is in I. We need to get that in B and A. So what we need to do is take the X minus the source rectangle. In this case, let's do B. So let's convert this to a different color. Let's use B colors. Let's actually use colors to identify. So we're using 12 for the X. So the X component, we need to do 12. And then I'm going to do actually red for the math. Sorry, my glasses got in the microphone. So 12 minus, and then we're looking at B here. So we need to get the x of B. So 12 minus 12. And that's by, so that's the x. The y of the intersecting rectangle, which is 26, minus the y of the source, which in this case is B, so that's 26 as well. And that equals B. So that comes out to be 0, 0. 0 by 0. So 0, 0. And that's at B. So, which we can see that because we can visually see it. That's the top left pixel of B. So we know that's correct. So now we need to do A. Alright, so that's going to be 12 minus 0. Okay, oop. A is white here. 12 minus 0. And then that is red as well. 12 minus 0 by, or comma, either one. 26 minus 0. That is going to equal A. So that turns out to be 12, 26. And that needs to be in white. So we're looping through every pixel in I. We're using I as the looping source. So now we need to convert it to B. Convert it to B here and A here. B here, A here. So we need to convert this pixel 12 by 26, this pixel here, to B and A. Once we do that, we can get the pixel, we can actually get the color data from 0, 0 in B and 12, 26 in A. Then we compare those values and we're done. Now we need to do the same thing, but I'm running out of colors here. I'll just do this. Let's do this in one more place here. Alright, let's green here. So let's use B for example. 12 minus 12 comma 26 minus 26. Alright, so we're looping through every pixel in A, or imagine in the intersecting rectangle. We're looping through every single pixel in this rectangle here. Every single pixel. So the only thing that's going to change is this and this. We're still going to subtract by the same value and the same value. So that becomes 13 minus 12, comma 26 minus 26. That will turn out to be 1, 0. So that's going to be a different part in B. So 1, 0, and that will be this one here. So once that's done, we would have investigated 2 pixels. So this is the algorithm and mathematics behind per pixel collision detection. And I took it a step further and I introduced an intersecting rectangle. That way we don't have to do matrix transforms. Or you could do this similar math involved with the other way, but the intersecting rectangle makes sure that you're doing it in a small scale, just what has intersected. You don't have to loop through every single pixel in B. You don't have to look at this pixel down here. Or you don't have to look at this pixel in here for A. Just what is intersected, just this area. Because that would be a very small, and you know those pixels exist in both textures. That intersecting rectangle exists in both A and B. So I hope you will enjoy the programming side of it. I hope you enjoy the mathematics and overview side of things as well. I'm still getting a little used to the Autodesk sketchbook, so I'm going to have to do some rough cuts during the video editing side, but hopefully you understand things, and once we get into matrix transforms, I will discuss things, because we're going to have to redo this, we're going to have to redo the rectangular collision detection and per pixel collision detection after we do matrix transforms. So I hope to see you next time. Thanks for watching.